Hello, everyone. Welcome back to the lectures of Professor Leach. Could you please confirm that you can hear us and see us as well? You could maybe write a message in the chat.
Yeah, that's a good idea.
Oh, that's fantastic. Thank you very much, Lindani. So we are here in the lecture hall of Stellenbosch University, where lectures start 10 minutes later than usual. So we will not be starting at 2 o'clock sharp. We will start a bit in a few minutes rather.
Yes, very clear. Who is Belinda?
Sorry?
Who is Belinda?
She's one of the NITheCS personnel. She helps with electronic.
Okay. Right.
Is that? Yeah, thanks, Roy. Oh, it's got to fit you.
Huh?
How are you? What's the chair?
Oh, well, thank you. How are you?
Okay. Roy is going to fit you.
Really?
Oh,
Thanks. Right.
Well, you better go back so we can collect
no,
it.
but there's a danger that this will continue. Definitely. So really message him, rather.
This is only one corridor for me.
Okay.
What?
Chris, would you like to do the welcoming for today?
It's okay.
Sure.
Yeah.
Okay. Kasana, would you like to welcome the online audience today?
No.
No? Okay.
Oh, it would be terrible.
Why do you say that? Did you check out the video of our show?
Yes, I did.
The song, everything was fantastic. The song was amazing. Okay, so welcome back, everyone. This is the second lecture of Professor Leach in the Mini-school. We are going to start in the next second.
When is the next second?
Right now.
No, it has to be after that. No. Okay, don't tell me you haven't got your notes from last week. You have?
Last week?
Yes. Remember last week?
We looked at the generator, second extension of generator.
Yeah.
was
I think now, just remember, when we're looking at x double dot equals naught or y double prime equals naught.
Y double prime.
Ah.
equal to 1.
And we have number 1, number 2, number 3, number 4. Well, now I remembered how to count, and someone remember what the gammas were.
You already fixed.
Now, I can take a guess at one of them, it would be day x.
Yes. Then one is d over dy,
Sorry?
d over dy.
I didn't.
Partial derivative with respect to y.
You mean day y? Well,
Yeah.
you say something funny, don't you? You say do.
Yeah.
Yeah. I usually use that for banks. Well,
Then
we don't expect me to remember them all, do you? Perhaps I should give you a classroom exercise to calculate them.
yes. That might
That's
be.
why I didn't bring any paper.
Oh, we could calculate without the paper.
Well, let's see now.
It's-
The x day one,
Yes. And then also y. Y.
One.
No. Then this one I've forgotten. One of them is xy dot x
x, y, and x.
plus y squared or y plus y squared.
On y squared.
Yes.
That's not really bad.
And the other one is xy.
Okay.
Yeah, xy dot x
But that-
plus x squared.
There we go.
You take x, y, x plus
X squared.
x squared.
Yeah, I guess.
That,
Yeah, I guess.
well, I'll leave it to you as an exercise to work out the remaining ones. Now, I think we worked out the commutators.
No, we didn't.
You didn't?
We didn't.
Sure we did.
Did we? No, we didn't.
Or did we work out the Lie brackets?
No.
I'm sure I mentioned them. That
You did mention them, but
You mentioned Lie brackets, but we didn't.
But to find what it was, if I remember rightly. It was gamma I, gamma J. So it's just like, sorry, just like a commutator. Now, if you take the Lie brackets, what are you going to get? So you get closure. All right? You understand that? You know all about algebra, don't you? Good. If you've got a question, ask. If you don't follow something, tell me. I'm not very good at reading minds. So we take the Lie bracket, and if we take all the possible brackets, of which there are quite a few, each one will either give you one of the 8 brackets, one of the 8 operators, or 0. For example, if we take gamma 1, gamma 2, obviously it will be 0. But gamma 1 with gamma 3 will not be 0.
Maybe can you perhaps like take an example, one of the brackets,
All right.
like how it works?
Okay. Let's try. Okay, which one would you like to take? You have to take 2. Give me 2
Maybe gamma 1, gamma 3.
and 3.
Yeah.
Okay. So if we do that, we'll get 3y plus x j 2 the x j y minus x j 2 j y j x. And what do you conclude from that? I'm sure you'd be.
Sorry, I couldn't follow that. Where do we get the delta over dy on its own?
Where are we? No,
On
sorry.
the second line. Where do you get the first term from?
I differentiate this with respect to x.
Of course, yes, sorry, yeah.
Yeah. Right. Don't you think you'd be better sitting there so that you can see?
Maybe, yeah.
There's no need to be so shy. You could have sat there. No, it's just then I don't have to sort of keep running the risk of spinal damage. All right. So we have that, and with a little bit of mental arithmetic, this will be just a y, and I have it there somewhere.
Gamma 2.
Oh, yeah, thanks. Now, you can do that for all of them. Obviously, if you had some of them, I can't see one offhand, but it probably is. Oh, for example, gamma 1, gamma 2. You take that Lie bracket, what do we get? A very fundamental number. No, you have to speak up. No, I didn't hear what you said.
Biggest at 0.
Yes, obviously 0. Yeah. But please speak up, because we're a long way away. So some will be 0, some like this one are not 0. Altogether, Now, you know all about Lee, don't you? Why is there so much silence? Right, do you know when he flourished? Don't they teach you anything in this place? Late 19th century. No? Do you know where he came from?
Norway.
That's that one, isn't it? Right. And he thought of all of these things. Well, you know why he thought of them? Have you ever been to Norway? You know anything about Norway? It's also got a horribly long, cold winter. So you have to go and think of something. Now, yes, so what is the algebra? It's SO3R. The SL stands for special linear. You know that. Very good.
Can I ask a question, please?
No, no, you can't. You say, Tommy! Right, come on.
I will tell you, I will say so if I'm not satisfied with the answer. The identity operator is also included or not?
No.
No.
No, I can't remember what the last two are. No one will tell me.
So are we claiming here that each of the gammas will arise as a Lie bracket of the other two? Because if we're taking the set of all Lie brackets, aren't we running a danger that we might miss one of the gammas because we can't express them as Lie bracket of some of the other two gammas?
Well, that's all right. You don't have to.
Okay.
Then it's a linear combination. Not that
Well, you can get a linear combination, that is true.
then the Lie brackets of any of those 8 generators gives you a linear combination of the elements.
But can we recover each of the other ones?
No,
Because it seems like we're restricting here specific to this set of Lie brackets. Or does constitute mean that we have to still take the linear combination?
no, he's saying that this Lie algebra is isomorphic to SL3R.
But why is it this? Does it say the set of Lie brackets?
Well, because you have a whole collection of Lie
It's
brackets.
bad English. You're right. you should say the Lie algebra, not the set of Lie brackets.
It's not only that the values of those brackets that we are considering, right?
Oh, I see.
That would be the first derived Lie algebra. It's not what you mean.
All right.
You meant to say the Lie algebra. I mean, he's correct in the sense that if you take that basis and then you take the Lie brackets of those bases and you think of a Lie algebra just in terms of basis vectors, then then in terms of that basis, that's the Lie algebra of the basis. That the brackets that the standard basis of SL3R gives.
So we take linear combinations of these ones as well as the Lie brackets.
No, just these ones, the 8-dimensional vector space.
Okay. Because it's closed on the Lie brackets.
And the Lie bracket of any two of these vectors gives you
A linear combination. Okay. Thank you.
You right?
Yeah.
Good. Maybe you should take over. You know what's going on now. Right, so this is a particular representation of a particular Lie algebra.
G7 is y del x.
Ah,
And then G8 is xy del x. Sorry, no, you've already got that one. X del x plus a half y del y.
Thanks, Bruce.
From your own paper.
Like for G6 is the other way around. Yeah.
No.
Yeah, for G6, for gamma 6, x squared has to go with the,
It should be x squared del x
yes,
plus xy for gamma 6.
for gamma 6.
Is it not possible that both of them will work?
Back in front.
Yes.
Right.
But it's possible that both different bases, right?
I think that's different.
Okay.
So you want the x squared here?
Uh,
I think
yeah.
Oh, sorry. What did I have to?
No, that's x1.
No, you want,
It's the gamma 6.
you want x squared here?
Yes. And xy there.
X squared.
Okay. Yeah, that's more symmetric. That's more symmetric to gamma 5.
Oh, yeah. Right, now, this is just one particular differential equation. And it would be fair to say it's a fairly elementary equation. But all linear Now, it doesn't matter what the equation looks like, as long as it's linear, second order, has 8 symmetries. Now, what does that mean? There's an implication. It means you can transform from one equation to another equation.
Are you saying that all second order linear DEs
See what it said?
have SL3R as the Lie algebra?
Which means
Yes.
The transformation.
all
is
second
to transform
order
the equation.
differential equations, linear, are actually just right off the prime equals naught in drag.
It won't be an isomorphism anymore, maybe.
Yes.
Well, at least too smart. That's an interesting result. Now,
Before we go into that, can I ask a question for clarification? So these operators, gamma 1 up to gamma 8,
yeah,
what do they leave invariant exactly?
the equation.
Are we claiming that any operator that leaves the equation invariant will be a linear combination of these?
No, that's a little bit too wild a statement. Because you could have a contact transformation.
So then what is the more restrictive condition that defines precisely these 8 and their
They
linear
have to
combination?
be point symmetries.
What is a point symmetry?
We got 8 of them there. Take a guess. It's expressed in terms, the coefficient functions are expressed in terms of the dependent variable and the independent variables. Now, if you want to go and have a more general symmetry, you can have dependence on derivatives, or you could have dependence on integrals. Right? Becomes messy, but you can have it. And that's really what it is. So you can generalize, not necessarily happily, but you can generalize things.
So I still don't understand what makes this 8. You said that I should take a guess, but I'm not seeing what makes the 8. Why is it 8?
You're saying that's the Lie algebra of the symmetries of the equation, provided you restrict yourself to point symmetries.
So that's the concept I don't understand. What is the point?
He means that we're going to make a change of variables. So at the moment we've got x and y.
Yeah.
X is our dependent variable.
Yeah.
Sorry, x is our independent variable, y is our dependent. And we're going to make a change of variables to, let's say, u and v,
Yeah.
which are functions of x and y.
Yeah.
In principle, you could have a function which is a function of x and y and dy by dx.
I see.
We're not allowing such
Okay.
transformations.
And why is it obvious that it should be 8 if we're
Well, it's not obvious. That's
Okay.
our first results.
Okay.
The only thing we've proved so far is just that the Lie algebra of that particular DE is this particular Lie algebra.
Maybe if you could start with the generator and then show us like how do you get to the gammas?
Want me to show you how to use them? I thought you were going to do that as an exercise. Yeah.
No,
Don't worry, we'll get there eventually.
But thank you, Bruce.
Right, so you're happy?
I think so, yeah.
Right. Why it has to be 8 is an open question. It is 8, that's it. Now, there are some equations which, of course, which are second order, but they're not linear, and they will have 8 symmetries. And what does that mean?
We get
When I talk about point symmetries, I'm talking about point symmetries, not just linear symmetry. That means that you can transform to the simple equation. Now, if you have a nonlinear equation, when you think of a simple nonlinear second order equation,
XY double prime equals 0. Maybe that's not a good one.
that's linear. Even I know that.
Oh, sorry. Of course it's linear, yes.
I'll give you a simple example.
Y times the Y double prime.
Huh?
Y times Y double prime equals 0.
Oh, that's a bit too simple. Let's take this one. Right? You see, your y double prime, you just cancel out the y. Here you come. Now, this equation is actually quite a famous equation.
Is it Bernoulli? No.
Huh?
I mean-
Well, it's more general form. I've given the simple form.
Okay.
If you take, let's see. All right, this is just a little aside. H double dot plus omega squared of t x. I think it's equal to 1 on x cubed. Now, that's a more. Right? This actually, even though it's not linear, still has 8 symmetries. Now, where would that, I'm talking about the x equation now, where would that arise?
In terms of application,
Yeah, I suppose you could call it application. Well,
it's inverse square, similar to inverse square force law, but it's just that.
how about you think in terms of more than one dimension? How about motion in a plane? See, if you had, let's see, what have we got? Right. If you had, I'll double up, plus omega T R is equal to 0. Right? Now, we're just talking about 2 dimensions, don't complicate life and make it in 3 dimensions. You can then separate it into a radial part and an angular part. And the angular part will lead to an integral. Because I hope the mechanics isn't getting too much for you.
It is.
It is. Okay.
Because the force is, because it's rotationally symmetric, the force is always directed towards the origin, isn't it?
I hope so, yes. Otherwise you'd be in trouble. You'd have such things flying off at tangents, I suppose, wouldn't it? Anyway, that's the type of problem. And when you separate it into radial and angular parts, you end up with something that looks like that, with a bit of omega squared thrown in there. Now, oh, sorry. I should try to learn to not get out of focus. The question is, how many symmetries would this equation have? Well, I'm going to leave it to you as an exercise. And of course, if you're sensible, you will look up the symmetry calculating package in Mathematica to save you a long calculation. You do use Mathematica, don't you?
I do.
Oh, right, okay. Well, Bruce, it looks like you'll have to show them how to do it. Now,
So I have a question. Isn't it still going to have like 8
well,
generations?
this one,
Yes.
why would it have 8?
Because it's still
No.
something of second order.
It's in 2 dimensions. This was in 1 dimension, right? Just space.
Yeah. Why
Right.
was in configuration?
So, if you,
Oh, there is T.
uh,
I see.
now, I think actually you probably do well to work out the symmetries so that, well, for this one, the other one's a bit complicated, but it is an important problem. Why is it important? Oh dear. It's a trouble for you young
It's the
people.
Kepler problem, isn't it?
No, it's not the Kepler problem, but at least you've got an idea of a problem. The motion of a charged particle running around in a circle. You can get things with magnets to make that happen. The magnetic field is varying with time, that's why it's omega squared of t. And that would be the radial equation. Now, question. Who would care? Oh, dear.
People at CERN.
Sorry?
People,
Hardly.
people at CERN.
I don't even think CERN was established when they did this.
Okay.
But maybe. But they would if they were around. Yeah. But you've got a pretty good idea there, because it wasn't at CERN, it was at another place in the United States. Now, do you know a famous laboratory in the United States? No? Ever heard of Los Alamos? You have.
From you,
What happened at Los Alamos?
you worked there once.
Speak up!
You attended, I think, a conference there.
Yeah, I wasn't thinking of what I did, I was talking about what happened there. And it was actually when I was about that big, so. You know where it is? Well, it's in the States, but Los Alamos doesn't sound like an English name, does it? So where would you think it could be?
California.
Sorry? Don't mumble.
California.
Well, you're getting close to New Mexico. Now, what was the advantage of having a laboratory in New Mexico when I was a little boy? I'm talking about the early 40s, in case you're wondering when that happened.
It was in the middle of nowhere, is it there?
Yeah, to
Actually, to say it's in the middle of nowhere,
We're
it's
recording
really
this.
being very precise about it. It is in the middle of nowhere, and it's a long way from the Pacific Ocean. No, oh, sorry. It's still as long. Oh dear, we've got Trump talking to me.
He found out that you were referring to something about USA, so the news page that popped up.
Yes, it happens all the time. And funny enough, Trump seems to appear in a lot of these pictures. Can't imagine why. It's not really very photogenic. Anyway, you're wandering off the point. What happened at Los Alamos in around about 1943, 44?
Maybe preparing for the World
Don't
War.
mumble.
Oh, yeah.
Preparing for the World War.
No, they'd already started the World War a few years ago.
Testing the atom bomb.
Right.
Okay.
Yes.
Yes. That's where they developed the atom bomb. And they had this laboratory a long way from the coast. And I can assure you, when you get to Los Alamos, it is a long way from everywhere. Why?
So the Russians wouldn't find out. I mean, not the Russians, the Germans
Well,
and the Russians.
No, it was the Japanese. We're
And
talking about the
Japanese.
Pacific, right?
Yeah.
Well, yeah. They wanted it to be out of range of Japanese bombers. So if you had it in California, it wouldn't be far enough. But I can assure you, once you get into New Mexico, you're a long way away. And so it was safe from being bombed. It was a good place to live. It was. Bit dry, of course. Now, they developed the atom bomb there. And of course, you know what happened. That basically ended the war. Well, if it didn't end the war, it certainly prompted its earlier cessation than would have happened.
It also killed a lot of people.
Sorry?
It also killed a lot of people.
Oh, yes, yes, well, bombing actually tends to have a bad effect like that, though.
Unfortunately, yes.
Yes. In fact, one of the advantages of living where I was as a little boy was that I was so far away from anything that I would have been quite safe. But they actually managed to bomb Darwin. That really got people mad. You know where Darwin is?
In Australia?
Australia has an area just under 3 million square miles. Can you be a bit more specific?
I'm not sure, more specific than
Up
Australia.
top,
Uh,
right? You know where New Guinea is?
yes,
Right, it's just across the water from New Guinea. Right. Unfortunately, I was in Melbourne at the time, and as you know, Melbourne is way down the bottom, so I was a couple of thousand miles away. This was a big thing. But some people actually had air raid shelters. I remember. And of course, once you build an air raid shelter, it tends to be a permanent feature of your garden. And you put petunias and things on top of it. You're supposed to smile at it. You do know what a petunia is, don't you? You're joking. It's a flower.
But Peter, it's only fair we don't know these things because you don't use a cell phone. And we have, each of us have a cell phone in our pockets.
Yeah. But
So
still,
there needs to be some balance, you see.
yes, but wait a minute. You don't know what a petunia is. You know what a dahlia is. Speak up.
What?
A dahlia.
I know what a dahlia is.
Oh, good. We can tell Bruce because he's not too sure.
Simon knows what a petunia is. She's very good with flowers.
Okay, I know what it is. I just didn't know the name.
Oh, all right. All right. Why do you keep wandering off the point? Anyway, where was it? Oh, yes, we were in Los Alamos, where they built the atomic bomb. I think they also built the hydrogen bomb there, didn't they? Yeah. But they have two sections in Los Alamos. They have the, what you might call the bomb section, I'll call it, where they do defense stuff. And then they also have another part, which is open to funny people like me. And that is where they were working on the peaceful use of the hydrogen molecule, not molecule, not atom. Keep going smaller.
subatomic particle.
Nucleus.
Oh, yeah.
And anyway, they had these very nice machines for accelerating particles. And one of them was just made it go round and round and round like this, sort of keeping on changing the magnetic field, so it went faster and faster. And what would you do then?
Smash it into something.
I think you've been there. You're quite right. You put in a target and you see what happens. And say, oh, that's interesting. Now we can go and have a cup of tea or coffee, whatever it is they have. So, all right. So this equation describes something. Oh, sorry. Now, can you imagine what it describes? Well, I'm giving you a chance to think. Oh, come on. Well,
So,
let's try another one. What does that describe? It's about the simplest equation you can come across.
Harmonic oscillator.
Right, it's the harmonic oscillator. Because you notice I didn't put a T in there, so it's just going, it's like you can think of the string, elastic string. You pull it down a bit, and then just pom, 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 pom. Okay. But now, what happens if your support is not very good? It's a bit loose, and the string starts to slip through. Right. What does the omega depend upon?
it depends on
Don't mumble.
tension.
Time, no? Is it tension or time?
Time.
Time.
What?
Time.
Omega doesn't, there's no T in there.
That.
No, I'm talking about this omega.
Oh,
Does
that's tension.
it depend on the tension of the string?
The length of the string, the gravitational constant,
See, there's someone who
and
will
the
do
mass of
mechanics
the
well.
bar.
Elasticity of the string.
So,
Root 2g over m.
very good. It'll take me half an hour to work that one out. So it depends
Sorry.
upon what might call the geometry of the problem. Now, you do accept that gravity being part of general relativity is just a geometric phenomenon. You know all about general relativity? Roy, do you know anything? No, I'm being serious. How long has general relativity been around for?
But general relativity is a theoretical physics topic.
I've heard of this, but I've
No,
never studied it.
didn't you do really applied mathematics?
We don't do general
Not
relativity
really.
in applied mathematics.
We don't have to do applied mathematics at undergraduate.
Even if you
Students
did
can
it as
choose.
undergraduate, it would be a master's level course.
Yeah,
Well, times have definitely changed.
unfortunately, yeah.
No, it was a third year topic when I was a boy.
Mm.
We did special relativity.
Oh, that's complicated.
Yeah.
That's special. Right, now. So here's this depends upon the geometry. That's in one dimension. If you have several dimensions, you then have a vector equation, and if the length of the string is not constant because you didn't build it up properly, the omega will depend upon time because the string is slipping through. And in principle, of course, you could say, well, we'll stop it from slipping through. How would you do that? Apart from dealing up the clamp.
You can let it run all the way out and then eventually it'll hit the floor.
No, you just grab the string and pull it out. No, simple. And if you could go and get the right balance, it would be a constant. And then you'd have a simple harmonic oscillator. But that's too simple for words, isn't it? So we have that, and we're sort of wandering off the point, which was, what happens if you have other equations? Okay, let me give you another equation. How many symmetries was that though?
Peter, can we write here, please?
Sorry?
Can we write in this center, please?
Oh,
For the sake of camera.
it's impossible, is it? Okay, what equation was I writing?
Shall I give you a better pen?
Now, we're talking about point symmetries, remember? Only point symmetries. How many symmetries will that have?
I'm not sure. I'll guess 1.
Not quite, that's correct. Well, you should work this out as an exercise. It has an infinite number of symmetries. So if it said 0, just divide it, sort of take the reciprocal, you would have been better off.
I mean the generators. It's gonna
Yeah, I'm talking about, when I say a symmetry, I'm talking about the generators of infinitesimal transformations,
Okay.
point transformations. Now, okay, so that has infinity.
What are they?
What?
Let's do that exercise. That's interesting.
Now you're doing the exercise. I double primary control. Hey. I want that white triple primary control.
Maybe 2 then.
Yeah.
2?
Yeah,
No, it's more than 2.
more than 2.
4.
4. Excuse me.
I don't think it's an even number. Actually, I can't remember, to be quite honest. So it looks like you'll have to work it out. How are you going to work it out?
Then calculation and stuff.
You have Mathematica?
Oh, yes.
Hmm?
Yes.
Well, you just go in there, you look for a program by Stelius Demas and someone else. There's no much forgotten. And you can do it. Simple. Boom. And then you can come and tell me the answer. I have a suspicion it's 7, but I could be wrong. That's why I'm not writing anything down. Now, if you go up to 4th order equation, you get the change again. And when you, apart from the first and second order equations are what you might call exceptional. Higher order ones, there's an actual pattern, which I can't remember. But you can check it quite easily. Just use the program I told you about, do it for a couple of them, and you'll be right. I think it's 7, actually. But let's put 7 as a question mark. So the second order equation is a bit exceptional because it has the extra symmetries compared to the general pattern. Of course, the first order equation is not self-playing crazy, so it doesn't really count. Now, why is there an advantage with so many symmetries for a second order equation? Have you ever heard of a guy called Isaac Newton?
Yes,
Right.
we haven't met him personally, but we've heard of him.
Yeah, well, it's a bit hard to meet him these days.
Okay.
At least not in this world. Now, what he did lots of things actually, but one of the things he did was to have his laws of motion. And the interesting part about it was a lot of mechanics, and when I say mechanics, I mean anything that can be vaguely related to motion is basically second order equations. So it's nice to have a lot of symmetries, potential symmetries anyway, because of the simplicity that you get using symmetries. Now, how do we actually use symmetries though? You seem to have been avoiding this one. Yes, you'll see you'll agree with me. Well, I'm waiting for a suggestion. How would you use them?
Well, the general idea is to take a complicated equation and to reduce it to a simpler one. But the methodology is non-trivial. It doesn't follow from what you told us so far.
That's a very good statement. Right, well, let me.
Maybe we can do that next week, Peter?
Oh, we're running out of time, are we?
Yeah, we are. It's
Oh, yes, right. So, Bruce, you can remind me. It is your job because I have a very fragile memory. I don't know why it's so fragile. But you know why, don't you?
not fully.
Well, that's about as much as you need to know, I can assure you. All right. So next week, what are we doing?
We're going to show how to apply the symmetries to simplify the solution of the difference.
Oh, right, okay. Yes, and to go and show how you can do it, we'll even start with this complicated equation. And I hope that you all remember what the symmetries are, because we'll need them for doing our reductions. All right? Okay.
Okay. Thank you.
Right.
Are there any questions either here or online?
Well, I keep forgetting we're online. Oh dear.
It seems like there are no questions. So thank you everybody for joining. We will continue next week, the same time.
Right. And in the meantime, see if you can do all the exercises. In fact, we may end up using next week. So you can give me a demonstration of how to do the calculation. Okay. Right? Oh, good, thanks. Okay.